Hello everyone, my name is Zhimao Fan. It's my pleasure to share our research paper titled Compound Multi-Branch Feature Fusion for Image Deraindrop. This work was conducted during my graduate studies in the Department of Electrical Engineering at National Zhongxin University in Taiwan, and I'm currently employed as a R&D engineer in the Department of Digital Image Technology at ASUS. Here is the outline for today's presentation. First, I will provide an introduction to set the context for our research. Next, I will dive into the related works that have informed our study. After that, I will introduce our proposed methods. And finally, we will discuss the result of our experiments and conclude our work. First is introduction. Image Deraindrop is a specialized test in the field of low-level computer vision. Its aim is to remove raindrops from an image to produce a cleaner version. This test is often categorized as an ill-posed problem within the domain of image restoration. The following figure illustrates this concept. An image degraded by raindrops existing in the one domain X. After undergoing the image deraindrop process, also known as image deraining, the image is transformed into a raindrop-free version, which belongs to another domain, referred to as domain Y. In terms of contributions, we have several key points to highlight. First, we introduce a novel restoration model called CMF-net, inspired by retinal ganglion cells (RGC), designed specifically for the image deraindrop task. Second, we introduce mixed skip connection (MSC), a mechanism featuring a learnable parameter to integrate branch information efficiently. Third, we present a new loss function, which we call PS loss, that combines peak signal-to-noise ratio (PSNR) and structural similarity (SSIM) matrix. Lastly, our CMF-net exhibits competitive performance on a raindrop dataset, particularly in improving SSIM values. This suggests that our model's performance aligns closer with human vision perception. Now, let's move on to related work that has informed our research. First, let's briefly discuss retinal ganglion cells, as they serve as inspiration for our work. Humans are the final receiver of visual information, but the initial receivers from the real world are RGCs. These cells mainly come in three types: parvocellular cell, which called P cells. These are sensitive to the shape and color of images and make up 80% of all RGCs. Second one is corneal cellular, which called K cells. These are the smallest among RGCs and primarily respond to color change. And the third one is magnocellular, which called M cells. These cells focus on transmitting light or dark signal and are more sensitive to low spatial frequency compared to high spatial frequencies. And turning our attention to image deraining, it's important to note that most research relies on synthesized datasets like RAN13K and RAN100H. The test of deraindrop is a specific branch of image deraining. for which real-world raindrop datasets can be obtained. And now, let's dive into the core of our research, the proposed method. On this slide, you will see the architecture of our proposed CMF net. And there are four main highlights to our CMF net architecture that I'd like to discuss. First, CMF net incorporates three distinct feature attention blocks in each branch of its UNet structure: pixel attention, spatial attention, and channel attention. Second, we employ a residual attention module as improvement over the existing supervised attention module, achieved by removing the supervised loss calculation. Third, we introduce a mixed skip connection to replace traditional methods of aggregating or concatenating branch features. This employs a learnable coefficient for better integration. And lastly, we propose a specialized loss function that combines two metrics, PSNR and SSSIM, to produce perceptually accurate restored image. Our branch network is built upon a three-level UNet architecture as shown in this figure. The raindrop effect image first goes through a shallow feature extraction with a convolution layer to extract initial features for each branch. We employ different types of attention blocks as shown in figure A, including pixel attention, channel attention, and spatial attention. The pixel attention generates a 3D attention mask without any pooling or downsampling, retaining local information in the output feature maps. This block has the most parameter among all, aligning well with the pixels in RGCs, which make up 80% of the total. Conversely, the channel attention block mimics the characteristic of M cells, which have fast transmission speeds and low spatial resolution. CIP employs global average pooling to reduce the input feature from 3D to 1D, generating a 1D attention mask. And finally, the spatial attention block simulates K cells, which are intermediate in both transmission speed and spatial resolution among the three cells type. SAP generates a 2D attention mask and also employs either global average pooling or max average pooling to reduce the feature dimension to 2D. After the feature extraction process in the different UNet branch network, these extract features are fed into the residual attention module. This module is a modification of the original supervised attention module SAM, as this figure, where we have removed the loss calculation as indicated in this section of the figure. Additionally, we replace the 1x1 convolution in SAM with 3x3 convolution. In our CMF architecture, we introduce a mixed skip connection, MSC, to integrate the output image from the residual attention module of each branch. As shown in this figure, MSC features three input pathways and utilize a learnable parameter, A of theta, to optimize the entire architecture through backward propagation. The main pathway, which is the output image, from a pixel branch network is scaled by the parameter f theta. The other pathway, which are the output image from the channel and spatial branch, are scaled by 1 minus f theta divided by 2. Consequently, the output residual image, IR, from MST can be mathematically represented as here. In traditional image restoration tests, loss functions like mean absolute error or mean square error are commonly used. However, these pixel-based loss functions like L1 and L2 do not consider global image information and often result in over-smoothing issues. Various other loss functions have been proposed to address these, such as perceptual loss and compound loss, which combine multiple loss functions. In our work, we introduce a new loss function to optimize CMFNet end-to-end, targeting a balance between human perception and metric score. Here, X represents the degraded image and Y is the ground truth data. Our loss function consists of two terms, the PS loss and the age loss. The PS loss incorporates both PSNR and SSI metrics. The closer the deranged image are to the ground truth, the closer the SSIM value will to be 1. And by replacing SSIM in the numerator, the overall loss decreases. On the other hand, a higher PSNR indicates greater similarity between two images, approaching infinity for identical images. We place PSNR in the denominator to further minimize the overall loss. Additionally, we include an omega term to prevent another numerical issue at the start of training. Now we are going to the experiments we conducted to validate our proposed CMF architecture. In our experiments, we trained CMFNet using the Deraindrop dataset, which contains 861 training samples. We then evaluate the model's performance on a test set A consisting of well-aligned images. On this slide, you will see a table summarizing our deraining performance. We achieved state-of-the-art results, particularly in terms of SSIM value. This indicates that our model excels at generating perceptually faithful images. And now let's look at some visual results generated by our CMFNet. For those interested in further exploration, our model is available on the Hugging Face website, where you can test it on your own image. Additionally, we also propose solutions for image dehazing and deblurring on the website. Displayed here is a figure visualizing the features outputted by each branch network. It's worth noting that the pixel attention block has the largest number of parameters, enabling it to capture the most detailed features, including both low and high frequency information. This aligns well with the fact that P-cells make up the majority of RGCs. Similarly, the channel and spatial attention blocks are modeled after M and K cells. M cells are particularly sensitive to the low spatial frequency, you will notice that the feature maps in the second column are less responsive to high-frequency details such as edge and textures compared to those in the last column. Now let's wrap up with some concluding remarks. In summary, we introduced CNFNet, a network for image Deraindrop that mimic the multipath retinal ganglion cells of the human visual system. We also propose a novel loss function called PS loss, specialized design for general deraining tests, and introduce the missed-skip connection as a modern replacement for traditional skip connection. Our model has shown significant improvement in SSIM value on a Deraindrop dataset, thereby validating its capability to produce perceptually flexible restored image. For future work, we will attempt more different restoration tasks, such as image deep learning, dehazing, and straight line removal. We will also focus on reducing parameter of the model to achieve the real-time removal level. And we will attempt to implement modules inspired by other cells, such as rod cells and cone cells, which act as previous acceptors before RGCs. And here's a fun fact. The acronym for our paper title, Compound Multi-Branch Feature Fusion, CNFNet, actually comes from my own name, 直冒犯. Thank you all for listening. I'm your speaker for today, 直冒犯.